Hi, my name's Ewan, and I'll be going over my public lecture review for the science of origami, presented by Professor Zeb Rocklin. I'll go over the main points addressed in this lecture in chronological order. So to begin, the first thing discussed, other than the term origami itself, is the physics behind stretching and folding. So of course, origami is the art of paper folding, and the physics behind folding actually includes stretching and compressing. So here we have Hooke's law. We've used this in class for springs. It says that stretching a solid generates a return force. The less material, the less return force. So making something 10 times thinner would reduce the return force by a factor of 10, or say 1,000 times easier to bend. The next thing discussed was that a little bit of history of the paper being invented in China 2,000 years ago. Like I said before, folding a sheet of paper 10 times makes it 1,000 times harder to fold. But the world record for most folds on a single sheet of paper is actually 12, which is only made possible by using an extremely long, thin sheet of toilet paper. The diagram on the right shows how the layers of paper both compress in the inner layers and stretch on the outer layers as you fold it. So the physics of folding and by extension origami actually applies to many fields. Solar power deployment requires the use of solar panels, and solar panels need wide exposure in order to be efficient. But that costs a lot of space. So a solution became to fold them using origami-like techniques of creasing and hinges to ensure smooth operation. There's also a lot of consumer items that take advantage of folding to deploy and retract, such as foldable smartphones, cardboard boxes, tents, umbrellas, and even a Kevlar weave. Moving on to the structure of origami itself, mathematicians prefer origami to be structured in crease patterns. That is, flat sheets that show all the creases for the folds. There are two main types of folds, mountain and valley, and they're named as such because mountain folds bend up like a mountain, and valley folds bend down like a valley. Another aspect of the structure is the vertex. This is the point where the creases come together. So some scientists began to wonder how to determine if the vertex is flat foldable, and they wondered this because making a structure flat reduces the amount of space it takes. So two main theories were discussed in the lecture about this, Maekawa's and Kawasaki's. If I'm being completely honest, I still don't understand how they work. I watched that section a few times and I still don't really get it. But I did get some quotes that describe what they are. So for Maekawa, he said, if a vertex can be folded flat, the difference between the mountain and valley folds must be 2. And Kawasaki said, a vertex is flat foldable if and only if we can alternately add and subtract the angles between the creases to get 0. So reading them back, I guess they do make sense, but I don't quite understand the underlying math behind it. So besides being flat, another issue is dealing with spheres and roundedness. Paper, of course, is flat and spheres are round, which is a problem. So there's one thing that translates roundness to paper, and it's the Mercator projection on maps. It preserves the angle of the Earth, which is great for navigation, but this results in severe stretching around the poles. For example, because of stretching, Greenland is noticeably larger in a Mercator projection than it actually is in real life. So to add on that, there's this thing called Gaussian curvature, and it's the curvature determined using 2 perpendicular lines on a surface and measuring their bend. Origami is entirely composed of folding, so it's tough to see how a sheet of paper could possibly obtain Gaussian curves. But one way is to get the look of curvature with computer-generated crease patterns, which make complex folds far beyond what human hands are capable of. And finally, here's some real stuff just to make sure I actually went through everything that I needed to. The name of the lecture, Science of Origami by Zeb Rocklin. The main points, origami is a combination of math, science, and art, and it involves the folding of a sheet to make it smaller or larger. This fundamental concept of folding applies to many different fields of science, including physics, as seen with Hooke's law. It interested me in particular because I used to be somewhat of a hobbyist when it came to origami when I was younger. I never really understood the math, I just thought it looked cool, but this lecture was definitely interesting because it taught me a lot of the science behind it. Something interesting I learned is that determining whether a sheet can be flat folded is actually considered NP hard, aka it's very, very hard for a computer to simulate and calculate it, which is interesting because you know, without the context, it actually seems like it'd be pretty simple, but it isn't. And for my follow-up, or the expansion beyond the lecture, I was wondering how origami, or just the physics behind folding, could be applied to, say, like autonomous robots, or if it's already applied. Because from an outsider's point of view, the aspect of folding to create more versatility in size and flexibility seems like an interesting prospect. And I believe that's it. Thank you.